Will tomorrow's astronomy still be terrestrial? You know what? I think there is a disturbing threat looming over the survival of observational astronomy as we know it today. A threat that we humans are obviously the cause of. Obviously. What am I talking about? Two different problems, but they are advancing with a common front. The first one is always the same, the usual one. It comes from very far away and has to do with the night sky, which, seen from the Earth's surface, appears to be more and more cloudy and distant. In recent decades, human population growth, ever larger urban areas, and daylighting of industrial and commercial infrastructure have led to an explosion in light pollution, with a scientific, cultural, and emotional loss that anyone capable of distinguishing right from wrong cannot help but find unacceptable. To this slow but unstoppable metastasis is being added the sudden aggression of an entirely new phenomenon, the advent of mega constellations of satellites generically called Starlink. Hundreds and then thousands of bright dots that, moving in low Earth orbit, will disrupt astronomical observations in every area of the spectrum. SpaceX has already received approval for 12,000 Starlink satellites and is seeking approval for another 30,000. Other space companies are not far behind. The Starlink mega constellation alone would increase by more than 10 times the number of satellites currently active over our heads. And there's also the fact that by spinning on lower orbits, the newcomers are brighter than 99% of existing objects and more reflective than Elon Musk's engineers predicted. There is no astronomical observatory whose operations will not suffer incalculable damage from this swarm of locusts, even if it is the shabbiest little mirror of an amateur astronomer. However, some scientific initiatives will be affected more than others. We are thinking in general of surveys for the detection and cataloging of asteroidal objects dangerous to our planet, and in particular of the Vera Rubin Observatory under construction in Chile. With a huge field of view, its mirrors will be able to capture in seconds an area of the sky 40 times larger than the full moon and detect objects 10 million times fainter than the human eye can see. One study shows that at least 50% of all images taken as part of the Legacy Survey of Space and Time, the 10-year program that will take place at the Vera Rubin Observatory and capture 1,000 ultra-high-resolution photos of the sky each night, will contain at least a trace of a satellite, which will make them difficult to use. Will this be our future? Increasingly milky skies and annoying webs of light everywhere? What do you think? In front of this finger pointing to the moon that could also seem to be the finger of a nostalgic traditionalist, someone will certainly say that what we are experiencing is nothing more than an inevitable phase of technological transition, to which it makes little sense to oppose. And that in any case, the future of astronomy is all in what space telescopes, or even lunar telescopes, will be able to do, freed from the atmospheric cloak and indifferent to the annoying satellite swarms. Of course, in doing astronomy from space, the advantages are enormous. It never gets light out there. You don't have to worry about clouds, turbulence, absorption of wavelengths by ozone, sodium, water, vapor, etc., etc. You can observe anywhere you want, across the entire electromagnetic spectrum, and there is no atmosphere to block your view or interfere with the wavelength at which you are observing. And if you are willing to go further than low Earth orbit, even to the point of placing your instrument in a region of gravitational equilibrium, such as Lagrange 2, you have the luxury of shielding yourself from the light and heat of the sun with little effort. Just as the James Webb Space Telescope, the future king of space telescopes, will soon do. All of this is certainly true, to the point where a migration of astronomical research into space seems not only inevitable, but desirable. But there are also a lot of good reasons to wish the opposite, or to wish at least a bit of common sense in the choices for the immediate future. And from the heap, I have pulled out 6 reasons: size, reliability, versatility, maintenance, upgradability, costs. 6 good reasons, 6 parameters on which to set up an honest comparison between 2 roads that many want divergent. Let's start from the dimensions, that also in astronomy count a lot. In fact, the diameter of the mirror determines the resolution of an instrument. That is the ability to separate 2 punctiform objects angularly close, as well as the amount of light collected, on which depends the maximum magnitude attainable. Well, in this field, there is no history between the 2 categories. and it is very likely true, as stated by the famous British astronomer Martin Rees, that at least for the next 100 years, the mirrors of the largest terrestrial telescopes will have a diameter much larger than that of the best space telescopes. In other words, for a long time to come, exorbitant costs and engineering difficulties will prevent the construction of space observatories larger than those on Earth. A statement difficult to dispute if you think that the largest primary mirror ever sent into space was that of the Herschel Space Observatory, with a diameter of 3.5 meters, while currently the large terrestrial telescopes measure 8 to 10 meters. And this gap is destined to increase in the coming years, when the generation of 30-meter telescopes will become operational, diameters to which will be able to oppose very soon only the 6.5 meters of the James Webb Telescope, while for the future in the mid-30s, there was already talk of LUVOIR, Large Ultraviolet Optical Infrared Surveyor, a space telescope of 15 meters. Very big indeed, but still pretty small compared to the 39 meters of the ELT, which by that time will have been operational for about 10 years. Someone could object at this point. Space telescopes don't have seeing problems. This must be an advantage, or not. Sure, but it was only until about 20 years ago. We must not forget that the latest and most advanced ground-based telescopes all implement adaptive optics, a technique to instantly correct for the effects of atmospheric turbulence using a thin, flexible, computer-controlled mirror. Astronomers target a bright enough reference star near the object they want to study. The computer analyzes the incoming light to measure how the atmosphere blurs it, then tells the control system how to adjust the shape of the mirror to correct the image in real time. Because turbulence is constantly changing pattern and texture, such systems can go so far as to alter the shape of the mirror up to 1,000 times per second. And if no bright reference star is nearby, as is often the case, astronomers can simply project powerful laser beams into Earth's upper atmosphere and create their own reference light. In this way, the observation from the ground has become competitive compared to that from space. It's not like working without atmosphere, but it's very close. The old Palomar 5 meters for 30 years, the largest telescope in the world, in the pre-optical adaptive era had an angular resolution limited by the atmosphere to 0.5 arc seconds, while today the Very Large Telescope, 8 meters, the Keck, 10 meters, and Hubble reach all the 0.04 arc seconds. The last thanks to the absence of atmosphere, the other two thanks to electronics that dynamically moves the mirror, correcting the wavefront to compensate in real-time distortion. Once operational, the ELT will be about 10 times higher than Hubble in terms of resolution, 0.005 arc seconds, which corresponds to distinguish from a distance of 200 parsecs two light sources separated by 1 astronomical unit, or two sources 30 centimeters apart from each other from a distance of 12,000 kilometers, and will collect almost 250 times more light, or can get to see objects 250 times fainter, with a magnitude limit of plus 34 against plus 28, as to say that it will be able to investigate a universe hundreds of times larger than the one Hubble can reach. The second parameter to consider is what we could also call the business risk. How would you feel about building a large Earth observatory if, on opening day, there was a 1 in 100 chance of seeing it collapse? Kind of nervous, isn't it? Well, this is more or less the mood of those who for years put their heads and hearts into designing space missions, which then at launch will all have a not insignificant chance of exploding along with the carrier rocket. The larger the mission, the greater the cost of failure. The best example of this cruel Russian roulette is the launch of the James Webb Telescope, which at the time of writing has been scheduled for December 22, 2021. The French launcher is recognized as one of the most reliable, but its success rate is not 100%, but 97%. This puts us dramatically facing a 3% chance that the $10 billion costs of the Space Super Telescope could go up in smoke on the launch tower, and that, you will no doubt agree, is certainly not a good living. Versatility. This parameter is for those who argue that we could easily do without the Earth observatories and transmigrate all telescopes to space. In reality, many aspects of space exploration still depend heavily on data provided by Earth-based astronomical observatories. Some space missions, for example, require that the three-dimensional position of spacecraft be known with very high precision. The European Space Agency's Gaia satellite, launched in 2013, is still observing and will do so until next year, over 1 billion stars in the Milky Way to determine their proper motion, distance, and position. Well, to get this data with the necessary precision, you have to know its speed with a smaller error of 2.5 millimeters per second, and its position in the sky with a maximum error of 150 meters. A significant challenge given that Gaia is also operating at the Lagrangian point L2, 1.5 million kilometers from Earth. A challenge won mainly thanks to a methodical observation campaign carried out by a network of terrestrial optical telescopes, able to determine with due precision Gaia's position on the background of the stars. Essential data for spacecraft positions and trajectories are also obtained from terrestrial, optical, and radio observatories to determine ephemerids, the position of solar system bodies. This involves dedicated observing campaigns of solar system bodies over long time periods. Similarly, star tracker guidance systems for satellites rely on high-precision positions for background stars provided by data from both ground-based and space-based observatories. Another important role of ground-based observatories is to enable detailed characterization of solar system objects to support the design of space missions and also to provide complementary scientific results. Saturn's moon Titan was extensively studied using ground-based telescopes before and during ESA's Huygens probe landing on the surface. ESO's Very Large Telescope and many others were used to characterize comet 67P Churyumov-Gerasimenko before the Rosetta probe arrived with its Philae lander. In short, doing astronomy from space without ground-based telescopes is a bit like going into battle without having air cover. Then there's the maintenance item to mark another deep groove between Earth and space. If a component of an orbital telescope fails or wears out, what can you do? Nothing. Unless you want to resign yourself to spending an enormous amount of resources trying to fix it. Run out of coolant, you need to send a mission to restore it. Gyroscopes or other targeting mechanisms wear out, you need a mission to replace them. Do you have an optical component that degrades? You need to send a mission. Have you run out of hydrazine, the propellant used in most spacecraft for orbital and attitude control? Has there been a micrometeorite impact? Is there an onboard computer starting to go haywire? Or do you realize you've sent a telescope with an astigmatic primary mirror into orbit? Well, if you really want to save it, all you have to do is send a mission with a good pair of glasses. Provided, of course, that the instrument in trouble is the very expensive Hubble and that shuttles have not yet been scrapped, because otherwise you'll have to resign yourself to lose everything. All the more so if your instrument is operating in Lagrange 2, so far away from home that even sending a shuttle is impossible. But if something broke in a large observatory on Earth, well, even if it was on top of Mount Everest, you would have no problem replacing or repairing anything. And what about the upgradability issue? Those not in the industry don't even realize it, but when a space telescope is launched, the instruments on board are already considered to be obsolete. On average, it takes 15 years to design a Hubble-type mission, which means that all the electronic equipment and especially the imaging sensors integrated on board the observatory reflects the best available technology, but that of many years before. Suffice it to say that the largest sensor for imaging on board the Webb telescope measures 2048 by 2048 pixels, an array that today we consider barely acceptable for the camera of a cell phone. A large ground-based telescope will never have these problems, and its instruments can be upgraded whenever a technological leap occurs. An easy example of that is the Palomar. The 5-meter Hale telescope was the largest telescope in the world until 1948, until the admittedly unsuccessful Russian 6-meter telescope came into operation in 1976 and is still actively used today. For the past few years, it has been upgraded with infrared sensors and an advanced adaptive optic system, and even it's about to be equipped with an ultra-high contrast spectrophotometer, which should allow it to image exoplanets 100 million times fainter than its own star. More than 70 years of history, and probably Hale will arrive to celebrate the century, while the Webb telescope is expected to remain operational no more than a decade. And to end on a high note, there is also the question of costs. Without going too deep into details, it is enough to compare the total costs of the Webb telescope, $12 billion, or that of Hubble's $20 billion, including the cost of repair and maintenance missions, which cost more than $1 billion each. With the expense incurred to build the 4 8-meter telescopes of the Very Large Telescope, just $330 million, plus another $10 for annual maintenance, and only $1.5 billion to build the ELT, which, let's remember again, will measure a whopping 39 meters in diameter. There is no doubt that going into space is imperative that we cannot and must not disregard. Space is, after all, our only safe exit, and it is the only way we have to keep alive that idea of the frontier that humanity so clearly needs so much. But because of all the reasons stated above, giving up astronomy made from Earth seems at the moment something really unthinkable. And that is why we are following with particular interest the advent of large telescopes of the last generation, that with their discoveries will accompany us at least for this century. But also on this front, there is no news. The three surviving projects among those proposed more than 10 years ago, the Extremely Large Telescope ELT, the 30-meter telescope TMT, and the Giant Magellan Telescope GMT, are all more or less behind the delivery dates announced at the beginning of the works. The GMT, under construction at the Las Campanas Observatory in Chile, mounts 7 8.4-meter mirrors for an effective aperture of 24.5 meters, about 10 times that of Hubble. Its location, about 2,700 meters above sea level in the Atacama Desert, will allow it to operate in the optical and infrared with an extraordinary investigative capability. By July of 2020, 2 mirrors had already been completed, with 3 more in various stages of grinding, polishing, or testing. And the foundations of the huge structure that would serve as the dome were already set in Las Campanas. Since then, the project, which has been in the works since 2005, has almost completely stalled, both due to the ongoing pandemic and funding issues, causing the date of the first light to slip to 2029. The 2 other giant telescopes have taken a different path. Both the ELT and the TMT will in fact count on a light collector formed by hundreds of hexagonal segments mounted in a mosaic. Amidst ups and downs, the activities for the construction of the ELT are progressing not too slowly. In 2014, earthworks began on the chosen site, Cerro Armazones, a 3,000-meter mountain in the middle of the Atacama Desert. Originally created under the name OWL, the world's largest telescope was originally conceived with a diameter of as much as 100 meters, then gradually reduced to the current 39.3. If all goes according to plan, the ELT should see the first light in 2027, 3 years behind the original schedule. 6 more years of painful waiting. A wait that for the TMT is likely to stretch on indefinitely. The 30-meter telescope seemed destined to rise on the Hawaiian volcano of Mauna Kea, where it would have flanked its cousins of the Keck Observatory and Canada-France-Hawaii telescope. And the first elements of the primary optics were already being prepared while waiting to begin work on the foundations of the dome. The chosen site, one of the most famous in the world for sky quality, would have provided TMT with access to the entire northern sky, something none of the giant telescopes being built in the Atacama Desert can aspire to because of their southern latitude. But the site, as it would soon be discovered, also has the disadvantage of being considered a sacred place by the natives of the island, who resent the idea of building on Mauna Kea, other observatories in addition to those already existing. There have been protests and demonstrations, even violent, and the project, including court cases and pronouncements of judges, always disregarded, has dragged up to the present day in a sea of indecision, so that currently no work has begun and even is thinking of changing the choice of site and build the observatory on the island of La Palma in the Canary Islands. Obviously useless to try to understand when and if there will be the first light. For now, the TMT project seems to be the only one of the 3 giants to be strongly at risk of cancellation. Good news comes instead from the aforementioned Vera Rubin Observatory, which could be the real surprise of the future new entries. What distinguishes the Rubin Observatory telescope and makes it worthy of being in the list of giants is not the size. The primary mirror measures only 8.4 meters, but its ability to photograph with extraordinary speed large areas of the sky. Located atop Cerro Pecan in north-central Chile, the Rubin will take only 15 seconds to image a star field of 9.6 square degrees with a limiting magnitude of plus 27. Such rapid imaging will lead it to photograph the entire visible sky in just 3 days, thus recording every 3 days the smallest change in brightness and position of any object brighter than that magnitude. Rubin is the largest digital camera ever built in astronomy, with the size of a small car and weighing more than 3 tons. The 3.2 gigapixel camera will produce images so large that 1,500 high-definition TV screens would be needed to display one at full size. The computer software will initially process the images in 60 seconds, looking for anything that has changed in brightness or location from previous images of the same area. When it finds something, it will immediately send an alert to researchers for quick follow-up. Astronomers expect the Rubin Observatory to provide up to 10 million alerts per night, with an average of 278 per second during a typical 10-hour observing session. This will be a huge advantage for astronomers studying transient events such as stellar explosions that produce novae and supernovae. The Rubin Observatory should also be able to conduct a detailed census of small solar system objects, discovering up to 90% of all asteroids larger than 140 meters that are still unknown, and tens of thousands of trans-Neptunian objects belonging to the Kuiper Belt, as well as try to answer a question that arose very recently with the sudden appearance of Oumuamua, the first interstellar object found within our solar system. How many clandestine visitors are out there, and where do they come from? A question that perhaps the Rubin Observatory will be able to answer very soon, since most likely the first light of the instrument there will be already in 2022. In short, it's difficult to hide the impatience with which we are waiting for the arrival of these extraordinary and now mythological instruments, promised for a long time but always slower to materialize. One thing is for sure though, when those domes begin to open, the astronomy we know today will literally be torn to shreds. That's if in 2027 or 2029, or whenever the eyes of the giant telescopes don't open wide to a hazy sky continually crossed with streaks of light. If they do, these sacred monsters may never be able to achieve their scientific goals. And at a time in history when we are on the verge of answering a large number of mysteries, a combination of thoughtless and heedless forces threaten to derail our dreams, hiding the loss under the alibi of there is space anyway. Is it worth it? What do you think? And what to do to prevent it?